Dear student, I welcome you to this class in which we will discuss about the operational amplifier, and this lecture will cover some part of this chapter and the rest will be discussed in the next class. The topics that we will uh, cover in this lecture are here. Now, first introduction, then what is operational amplifier, its definition, then circuit symbol and IC pin configuration of OPAMP. After that, characteristics of an ideal OPAMP, then AC equivalent circuit of an OPAMP. After that, common mode rejection ratio or CMRR, and then OPAMP offset voltage. After that, input-output characteristics of an OPAMP will be discussed. Then slew rate, and after that, concept of virtual ground will be discussed. And finally, application of OPAMPs will be discussed, and the application will be limited to the following cases. Number one is inverting amplifier, then scale changer, phase shifter, non-inverting amplifier, unity gain follower or unity gain buffer, adder or summing amplifier, differential amplifier, followed by subtractor. Now, introduction section. Operational amplifier, which is abbreviated as OPAMP or OPAMP, is a direct coupled amplifier with very large voltage gain, very high input impedance, and very low output impedance. And these electronic device or amplifier can be applied to perform a wide variety of linear and non-linear operations by changing a few external circuit elements. And this type of amplifier is usable in the frequency range 0 to some megahertz. And OPAMP was first developed by Robert Whitler in 1964. And most of the OPAMP that we used are found in form of IC, that means integrated forms, and these IC form OPAMP are relatively low, have relatively low cost, and that's why they are very popular in the electronic industry. And I have already give you an idea that clue that OPAMP can perform a variety of mathematical operation, for example, addition, subtraction, multiplication, integration, differentiation, etc., which were used in case of analog computer. However, in the present days, the OPAMP can be used in case of voltage to current converter, current to voltage converter, and rectifier, comparator, etc. And also OPAMP can be used to fabricate filters, oscillators, etc. And since OPAMP perform two types of operations, number one is it amplify the input voltage and then some mathematical operations. So it is so named operational amplifier because it do two types of operations. Number one is mathematical operation and number two is amplification. And also negative feedback can be applied in operational amplifiers, and in case of negative feedback, the activity can be controlled exclusively by the feedback elements, but not by the active or passive elements. Those constitute an OPAMP. Now, what is an OPAMP? Already we understand that an operational amplifier or OPAMP can perform several types of mathematical operations. So we can say that an operational amplifier or OPAMP is an electronic device which can perform some mathematical operations, for example, summation, adder, subtraction, multiplication, integration, differentiation, etc. And this type of amplifier has a very high input impedance and very low output impedance, which has also very high bandwidth. And with this figure, this is a standard circuit symbol of an op-amp. Further, op-amp can also be used in case of signal amplification, impedance transformations, and in case of active filters, oscillators, voltage regulators, analog to digital, and digital to analog converters, voltage comparators, voltage to current converters, and current to voltage converters, etc., as well as half and full wave rectification in case of half and full wave rectifications also. So op-amp has variety of applications and which reach the electronic industry. And now we come to the circuit symbol and IC pin configuration of op-amp. And as we and you know that op-amp is in present day op-amp is very important and it is very familiar in the electronic industry, and this op-amp is available in different packages such as 8 lead to 1 in line package or TIP package with two parallel lines of pins as shown in this figure. And here this is DIP op-amp. Here two lines of pins here, and this is the broken end, or it may be a circle here, and this is the starting end, and the number of the pin will be proceeding this way: 1, 2, 3, 4, and then from here 5, 6, 7, 8, etc. And another kind of op-amp can be found, which is TO5 metal case. TO5 metal case, and this is shown here, metal case op-amp, and this is very costlier compared to the DIP. So in the electronic industry or in practical cases, DIP op-amps are mostly used, and the different pins of certain functions. And for example, here the functions of different pins are tabulated. First you see that 7 and 4. This 7 and this is the 7 and this is the 4. Pin number 4 and 7, and the positive power supply voltage is given to the pin number 7, and negative end of the power supply is given to the minus V is given to the terminal number 4. And terminal number 2 and 3 are 2 inputs. So in case of op-amp, there are 2 inputs, 2 and 3, and input voltages are given to these terminals or in these 2 terminals. And if input voltage is given to this terminal, that is in the pin number 2, keeping pin number 3 grounded, then the output will be inverted. That means the output will be out of phase of the input voltage. That means there is a phase difference of 180 degree. That's why this terminal, that means terminal number 2, is called the inverting input terminal, because it inverts the input voltage. And if you apply the input voltage to the terminal number 3, keeping terminal number 2 grounded, then the output will be in the same phase that of the input voltage. That's why it is called non-inverting input terminal. And the output is measured at across the pin number 6. Here is the output voltage V0, which is measured across the pin number 6. And then 1 and 5. These 2 pins are also important because ideal op-amps are actually in case of ideal op-amp, if you give equal voltages to these 2 terminals, then the output will be 0. That is, the op-amp will be perfectly balanced. But in case of practical op-amp, it cannot happen. And in that case, if you apply same voltage to these 2 terminals or grounded these 2 terminals, then the output, there will be some definite output, and which will cause error in the next operations, and this should make to 0, and that can be done by using our pin number 1 and 5, and the process by which the output can be made 0 for 0 input voltage is called the offset nulling. So pin number 1 and 5 are used for the offset nulling operation, and number 8, pin number 8 is kept has no connection. Pin number 8 has no connection, and no connection is given to this pin number. And now come to the AC equivalent circuit of an op-amp. Here is the first figure is the standard circuit symbol of op-amp, and this figure is the AC equivalent of this op-amp. And you know that the input voltages are applied to the terminals 2 and 3. You know that number 2 is inverting input terminal, and that's why negative sign is given here, and number 3 is the non-inverting input terminal, and that's why positive sign is given here, and the output is V0, and if you apply input voltages to both of the input terminals, then the output will be nothing but the product of the difference voltage of these across these terminals and the gain of the amplifier. That means V0 will be A into VD. VD is the difference voltage. That means the difference between these two voltages. And since this terminal gives the same phase, and this terminal invert the output voltage, that's why difference is nothing but V1 minus V2. So VD is equal to V1 minus V2. VD is equal to V1 minus V2. So the output will be A into V1 minus V2. Now, since this is the AC equivalent circuit of this op-amp, here the input resistance is given by Ri, and the output resistance is given by R0, and the output voltage V0 is measured across these R0, these resistance R0, which is nothing but A into V1 minus V2, where A is the gain of the amplifier. Now come to the characteristics of an ideal op-amp, and here the characteristics of an ideal op-amp are discussed. Now first, the open loop gain of an ideal op-amp is infinity. That means the ratio of the output voltage to the input voltage is infinity, and the input impedance of such amplifier is infinity, and the output impedance is 0, and the bandwidth of an ideal op-amp is also infinite. And further, these characteristics is most important because we will discuss this topic later. An ideal op-amp is perfectly balanced. That means if you apply equal voltages across the equal voltages to the inverting and non-inverting terminals, that means V1 and V2. If V1 and V2 are equal, then the output V0 will be equal with 0, and then it will be called perfectly balanced. In case of ideal op-amp, it is perfectly balanced, and the characteristics of an op-amp is independent of the temperature. That is, it is linear, and it does not, and its characteristics do not change or vary with the temperature. And the common mode rejection ratio, or CMRR, which will be discussed later, is infinite in case of ideal op-amp, and the slew rate is also infinite, so that the output can change simultaneously with the variation of the input voltage, and also the slew rate will be discussed afterwards. Now, although these are the characteristics of an ideal op-amp, but in practical cases, the practical op-amps do not obey all these characteristics. They deviate from these characteristics, which are listed here. Number one is, in case of ideal op-amp, you know that the loop gain is infinite, but in case of practical op-amp, it is not infinite. It is a very high value. It is somewhat like 2 into 10 to the power 5, and then the input impedance in case of ideal op-amp was infinity, but in case of ideal op-amp it is not infinite, rather than it is 2 mega ohm, although it is very high value, but it is not infinity, and then infinite. And then output impedance for of an ideal op-amp was 0, but in practical case it is not a 0, it is somewhat like 75 ohm. And the input offset voltage, that means input offset voltage is, what is input offset voltage? You know that if equal voltages are given to these two terminals, then output should be 0. And in case of practical op-amp, it is true for ideal cases, but in practical cases, although V1 and V2, you give equal if V1 and V2 are equal, but V0 will not be 0, and then a DC voltage will be applied across these two terminals in such a way that the output voltage V0 can be 0, and this voltage is called the input offset voltage, and it is nearly equal to 1 millivolt. That means you have to apply 1 millivolt a voltage, DC voltage about 1 millivolt across these two terminals, and then V0 will be 0. So for practical op-amp, it will be balanced when the input offset voltage will be nearly 1 millivolt. Now come to another important factor, another important topic, which is called common mode rejection ratio, or CMRR. So already we you know that ideal op-amp is perfectly balanced. That means if you apply equal voltages in these two terminals, then the output will be 0. But in practical case, you already know that the output voltage do not become 0 when these two voltages applied to these two terminals are equal or grounded. So in that case, that means in that case, whenever you get the output voltage does not exclusively depends upon the difference voltage which were applied to these two terminals, and that means and then the output voltage also depends on the average of the voltages that you have applied to these two terminals, and then the average of average of the voltages that you have applied to these two terminals is called the common mode signal. So whenever you measure the output voltage V0, it depends upon two types of voltages. Number one is the difference voltage, is nothing but the difference of these two voltages, and if you take that V1 voltage is applied to this non-inverting input terminal and V2 is applied to the inverting input terminal, then difference voltage is equal to, here given is Vt is equal to V1 minus V2. Here also it is V1 minus V2 is equal to difference voltage, and the common mode signal voltage is Vc is equal to V1 plus V2 by 2. That means V1 plus V2 is equal to Vc, and after simplification you can find that V1 is equal to Vc plus half Vt, and V2 is equal to Vc minus half Vt. Now if you consider that when these terminals, that means inverting input terminal, is grounded, then if the gain of this amplifier is A1 and you apply here the voltage B1, and if you consider the case when the non-inverting input terminal is grounded and V2 is applied in this terminal, then for the first case when this terminal is grounded, then you will get the output voltage output voltage A1 V1, and when this terminal is grounded, then you will get A2 V2. So here you can write that when A1 is the voltage gain when the terminal A is grounded, and A2 is that when the terminal B is grounded, then V1, then you can write V0 is equal to A1 V1 plus A2 V2, and you also calculate that V1 is equal to Vc plus half Vt, and V2 is equal to Vc minus half V1 is equal to Vc plus half Vt, and V2 is equal to Vc minus half Vt, and substitute these values in this equation here. Right, also here we calculate this is equal to this, and substituting these values of v1 and v2 in this equation, we get finally 2 vc into a1 plus a2 plus half vd into a1 minus a2, that is equal to AC Vc plus AT Vt, where AC is equal to A1 plus A2, which is called the gain for the common mode signal, and AT is equal to half A1 minus A2, which is called the gain for the difference voltage. And then in case of ideal op amp, this AD should be very high and typically to infinity, and AC should be very small and typically to be 0, but in practical case this does not happen. And then another term which is called the common mode rejection ratio, which actually determines the figure of merit of the op amp, and which is defined as follows. The common mode rejection ratio is equal to AD by AC, and modulus of AD by AC, and such a way that AD is very high and AC is very small, so that CMRR may be very high. And sometimes common mode rejection ratio is expressed in decibel unit, which is also given by 20 log 10 modulus of AD by AC. And for case of IC741 op amp, the CMRR has the value about 90 decibel. Now come to the op amp offset voltage, and already we discussed about what is offset voltage. Now in this topic, in this section, we once again will discuss about the offset voltage. And you know that when the two voltages applied to the non-inverting and inverting terminals are equal, otherwise they are grounded, then the output should be 0. But this is true for ideal op amp. But in case of practical op amp, this does not happen, and this does not happen due to the lack of symmetry of the constituting elements, as well as the mismatch in the constituting transistors connections. And in that case, the output V0 will not be 0 completely, and there will be finite value, and then the output voltage will be called offset voltage, offset output voltage. And this offset output voltage has the value somewhat like near in the order of millivolt, maybe 1 millivolt. And then to minimize this, you have to apply a DC voltage across these two terminals, and the input voltage, input DC voltage applied to the two input terminals, for which the output voltage becomes 0, is called the input offset voltage. So we learned from these discussions that two types of offset voltage. Number one is input offset voltage, and number two is output offset voltage. Now remember that in case of very large input voltages which are applied to the inverting and non-inverting terminals, then these offset voltage does not does not produce any kind of error because the input voltage is very high. But in some certain cases, for example, for low voltages, for application of low voltages across these two terminals, the offset voltage matters. And these before using an op amp for different kind of operations, one has to first perform the offset nulling. The process in which the output voltage, offset output voltage, is made to 0 is called the offset nulling, and this can be done by the two terminals 1 and 5, which I already discussed. Now we will learn about the input-output characteristics of an op amp. Here, this figure actually demonstrates the input-output open loop characteristics of a typical op-amp. And you see from this figure that that whenever the input difference voltage, actually here this axis difference input difference voltage is plotted. Whenever the input difference voltage is increases slightly, then the output increases drastically, and it becomes to a maximum value, which is very close to the supply voltage V, and this voltage is called V saturation. And after that, if you further increase the difference input difference voltage, the output voltage will be constant to the saturation voltage V saturation. And in the also in this case negative direction, if the negative voltage if the difference voltage is increases in this direction, there is a negative direction, and it will very very quickly reach to the saturation value. And this saturation value is very close to the applied supply voltages to the op-amp. That is, it is very close to plus minus V. And for you know that in case of IC74 on op-amp, the supply voltage is somewhat like plus minus 15 volt or plus minus 12 volt. So this saturation voltage is very close to plus minus 12 or plus minus 12 volt. This is plus 12 volt and this is minus 12 volt. Very close to these voltages. And the difference voltage, the minimum difference voltage at which the output will reach to the saturation value can be calculated by this relation. V minimum is equal to plus minus V saturation, that is the saturation of voltages, which is nothing but plus minus 15 or plus minus 12 volt for IC741 by A is the open loop gain. And in case of practical op-amp, you know that A has the value of the order of 10 to the power 5, and if you use this value in this relation, we get V minimum is equal to plus minus 12 by 10 to the 5, or it is equal to plus minus 0.12 millivolt. That is, it is very small value. So whenever you proceed or increase the difference voltage beyond 0.12 millivolt, then the output will reach the saturation value. Conversely, in case of negative direction of the voltage, that is, whenever you increases the voltage beyond minus 1.12 millivolt, minus 0.12 millivolt, minus 0.12 millivolt, then it will further reach to the saturation value. So, in case of linear operation, open loop. So in case of open loop, op-amp is unsuitable for linear operations. So we can understand that in case of whenever we use an op-amp, if we know the saturation value or the supply voltage value, then we can easily calculate these minimum value of the input voltage for which the output will reach to the saturation value. Now slew rate is very important, which will determine how fast the op-amp will operate, and it is defined as the maximum rate at which the op-amp output can change, and it is measured in volt per microsecond unit. And for IC741 op-amp, the slew rate is about 0.5 volt per microsecond. And an op-amp can be treated to operate very fast when the charging and discharging process or time for the internal compensating capacitor will be less than the output voltage, less than the time that we take for the changing of output voltage from one level to another level. So if one tries to drive the output of at a rate of voltage greater than the slew rate, then the output will be distorted. So an OPAMP be more will be will work very fast whenever the sleep rate will be very high. And in case of ideal OPAMP, you know that the slew rate is infinite, such that the output voltage can change simultaneously as the input voltages are changed. Now, concept of virtual ground, it is very important throughout this chapter to calculate different gain for different kinds of amplifiers. So now we come to the concept of virtual ground. What is virtual ground? And here a basic diagram. This figure is nothing but the basic diagram of a non-inverting amplifier. And here you see here that RS is the here R1 is the input resistance, and the inverting the voltage is applied. The input voltage is applied to the inverting input terminal, and the non-inverting input terminal is grounded, and the out a part of the output voltage is the feedback to the input terminal through the resistance R2, and that's why R2 is called the feedback resistance. And the negative feedback, in this case, negative feedback is applied, and the negative feedback is applied in such a way that the potential of the point A can be made to 0. And furthermore, since the input impedance of this op-amp is very high and output impedance is very low, we know these two things, and also the gain of the op-amp is actually infinity. Now we let the gain of this amplifier A, then the output voltage V0 will be A into Vi. Vi is the input voltage, and since A is the gain is infinity, so for finite values of V0, Vi should be 0. That means Vi tends to 0. Furthermore, as Ri is tends to infinity, so no current will pass through this op-amp, and that's why the potential of the point A is 0. And although the point A is not directly grounded, but its potential is equal to that of the ground potential. That's why the point A is called the virtual ground. So the word virtual is used to imply that although the point A is not directly connected to the ground, but it behaves like a ground point. However, it is not the actual ground. So this point, and we will see in future discussions that the point is very important for calculation of the gain of some amplifiers. Now here we come to the section in which the applications of op-amp will be discussed. Now first, the inverting amplifier, and this is the basic circuit diagram of an inverting amplifier, and you know that an op-amp will be act as an inverting amplifier when input will be given to the inverting input terminal, keeping the non-inverting terminal to grounded. And in this case, the input voltage Vi is applied to the inverting input terminal through a resistance Ri, which is called the input resistance, and R2 is the feedback resistance, and through which a part of the output voltage can be feedback to the input. Now let the current passing through the current passing is the current passes through the resistance R1 is I, and that passes through the resistance R2 is I prime, and then consider the point A. Here the point the current I is entering to this point and I prime is leaving this point. So if we apply Kirchhoff's current law, then you know that the algebraic sum of these two currents I and I prime will be 0, and this is as since this current is entering to this point, so it is positive, and since it is leaving this point, so it is negative. That means I plus of minus I prime is equal to 0, that is which gives I is equal to I prime. So we write here I is equal to I prime, and also you can say why this I and I prime will be equal, because no current will be passing through this OPAMP due to the very high input impedance. And also you know that the point A is the ground, a virtual ground, and which is discussed in this section. So point A is virtual ground, and then we can calculate the value of the current I and I prime from this circuit diagram. And now first we calculate that I, the value of I, and the value of I is nothing but the difference of the voltages of this Vi and the voltage or potential at the point A. Let the potential of this point is Vx. Then I is written as, I can be written as Vi minus Vx by Ri, which is written here. I is equal to Vi minus Vx by Ri, where Vx is the potential at A, which is nothing but 0. And also I prime is equal to the potential difference between these and these. That means Vx minus V0 by R2, which is also written here. I prime is equal to Vx minus V0 by R2. So from this relation I is equal to I prime, we can write Vi minus Vx by Ri is equal to Vx minus V0 by R2, or from this V minus V0, since Vx is equal to 0, so minus V0 by R2 is equal to Vi by Ri, or V0 is equal to minus R2 by Ri into Vi. And notice here, look here, that the output voltage has a negative, the right hand side has a negative sign. That means the output voltage that we will find at the at this terminal, that is terminal number 6, it has the opposite phase that of the input voltage. So in this case, phase has changed. And also the gain, from this relation you can find out the gain of the amplifier, which is given by V0 by Vi, that is equal to minus R2 by Ri. And as I said already, that the negative sign indicates that the output is 180-degree out of phase with the input. That is, the output voltage is in opposite phase that of the input voltage, and which means that means that the output uh, that the amplifier inverts the input voltage, and that is why it is called an inverting amplifier. And obviously the gain of the amplifier can be found out from this relation R2 by R1, and choosing R2 and R1 we can determine it, and it is, that means R2 by R1 or gain is completely unknown known quantity, because we can choose R2 by R1 as we wish. Now, scale changer, why an OPAMP is called, why an inverting amplifier is called a phase changer, that can be understood from this section. And we know that the output voltage from this relation, output voltage of an inverting amplifier is given by R2 by Ri into Vi, which is also written here, R2 by Ri into Vi, that is equal to, and you write R2 by R1 as K. So you get from this relation that V0 is equal to minus K into Vi, where K is nothing but R2 by R1, the ratio of the feedback resistance to the input resistance. And it is perfectly or accurately a known constant, because in implementing the circuit, you can choose R2 by R1 according to your willing. So thus the circuit, from this circuit the output that you will get is is nothing but the product of the input voltage and this constant K. That means the output voltage scale is obtained by multiplying the input voltage scale by the factor K, which is called the scale factor. And in this way, an inverting amplifier can act as scale changer. Now, phase shifter, the inverting amplifier can also act as phase shifter. Now, let the resistances, the input resistance Ri and the feedback resistance R2 are replaced by respective impedances Z1 and Z2, where Z1 is the impedance corresponding to Ri, and Z2 is the impedance corresponding to R2. Then the gain, that is V0 by Vi, can be written from this relation. V0 by Vi is equal to Z2 by Z1 minus with a minus sign. And now if you assume that the magnitude or amplitude of these two impedances, that means Z1 and Z2 are equal but phases are different, then you can write from this relation V0 by this relation. Here it is written V0 by Vi is equal to minus mod of Z2 e to the J phi 2 by mod Z1 by e to the J phi 1, where phi 1 and phi 2 are the phase angles of the output and input voltages. And since the amplitude Z2 and Z1 are equal, so you can write from this relation that V0 by Vi is equal to e to the power J phi phi 2 minus phi 1. Therefore, the therefore the inverting this inverting amplifier, in this case of inverting amplifier, the OPAMP can shift the phase of the output voltage by an angle phi plus phi 2 minus phi 1, and which can have any value between 0 to 360 degree. And however, in this case the amplitude remains constant. So an inverting amplifier can act as a phase shifter. Now come to the another application of OPAMP, which is non-inverting amplifier. Here is the basic diagram of a non-inverting amplifier, and you know that in case of non-inverting amplifier, the inverting input terminals is grounded and it is done through a resistance R1, and the non-inverting terminal and the input voltage is given to the non-inverting terminal. Here it is the feedback resistance R2 and the output voltage is V0, and you know that from the concept of virtual ground, the potential of this point will be that of this point, non-inverting terminal. So the potential of the point A would be Vi. You can you can understand from another way that since the input impedance of the op-amp is infinite or very high value, so no current will passing through this, and then the voltage potential of the point A and Vi will be identical, so almost equal. So the potential at the point A is also high. And you also know that or consider that the current passing through the resistance R1 is I, and that through the feedback resistance is I prime, and using KCL or Kirchhoff's current law, you can easily understand that I is equal to I prime. Further, since this is the input impedance of this op-amp is very high, so no current actually passes through the op-amp, so this current will be equal to this current. That means I is equal to I prime, and now I is equal to the voltage difference between these 2 points divided by R1. That means 0 minus Vi, since the potential of the point A is Vi. So 0 minus Vi by R1, which is also written as 0 minus Vi by R1, that is equal to minus Vi by R1, and I prime is equal to the voltage difference between these. That means Vi minus V0 by R2. So it is written as Vi minus V0 by R2, and since these two currents are equal, so this V minus Vi by R1 and this quantity will be equal. So we write here Vi minus V0 by R2 is equal to minus Vi by Ri, and from this relation after simplification we get V0 is equal to R2 into 1 by R1 plus 1 by R2 into Vi, and and from this relation further you get that V0 is equal to 1 plus R2 by R1 into Vi. That means V0 by Vi is equal to 1 plus R2 by R1. That is the gain in this case. Gain of the amplifier A is equal to 1 plus R2 by R1, which is somewhat different from that of that in case of inverting amplifier. Also, you notice here that the output voltage has the same uh, the same sign that of the input voltage. That means the output voltage is in the same phase that of the input voltage. So in this case, no phase is shifted in this case, and the gain is 1 plus R2 by R1. So in case of non-inverting amplifier, the output voltage is in the same phase of the input voltage, and in this case the gain is somewhat different from that of the input inverting amplifier. Now we come to the unity gain follower, and you know that, or you see here that the gain of the non-inverting amplifier is equal to 1 plus R2 by R1, which is also written here is equal to 1 plus Rf by R1. Now, if you consider that Rf by R1 is equal to 0, then A will be 1, and then the amplifier will be called unity gain follower. And in that case, since Rf by R1 should be made 0, that means Rf either Rf is equal to 0 or R1 is equal to infinity. And such a circuit diagram is shown here. Here, connecting wire is connected to the output voltage, which has actually zero resistance. That means R2 is equal to 0 here. And since OPAMP has impedance infinity, so input resistance here R1 is equal to infinity. So this diagram is nothing but unity gain follower or unity gain buffer. And so figure 7 represents a unity gain follower, and it has some applications. For example, if you wish to find out, if you wish to get an output voltage which is in the same phase and have the equal value or identical value that of the input voltage, then you have to use a unity gain follower or unity gain buffer. That means the input, this type of amplifier allows the input voltage to be transferred to the output without any change. And further, this type of amplifier can be used as an impedance matching device between a high impedance source and a low impedance load. Now we come another application of OPAMP, which is for the adder or summing amplifier. The basic diagram of a summing amplifier is shown here, and in this type of amplifier, the output voltage is made to the sum of the input voltages, and here the input voltages are applied to the inverting input terminal, keeping the non-inverting input terminal to the ground. And here the different several voltages V1, V2, V3, etc. to up to Vn are are connected to the inverting input terminal through the resistances R1, R2, R3, etc. towards to up to Rn. And let the current given following through the resistances R1, R2, R3, etc. are I1, I2, I3, etc. are In. Then the net current that will enter to the point I will be the algebraic sum of these currents. That means I is equal to I1 plus I2 plus etc. plus In. And furthermore, since this point is virtual ground, so the current I and I prime will be identical, and you also can find out the values of this I and this I prime from this circuit also. And now to calculate the value of I, you have to calculate the values of I1, I2, etc. Now I1 is equal to, given here I1 is equal to, what is I1? I1 is equal to the voltage difference between this voltage and this voltage, that means V1 minus the potential of the point A, that is nothing but 0. So Vi minus 0 by R1, that is equal to V1 by R1. Similarly, you can find out the values of I2, I3, etc. And then I2 is equal to V2 by R2 and dot dot, and In will be Vn by Rn. So I will be V1 by R1, V2 by R2, dot dot, Vn by Rn. Further, I prime can be found out from here. I prime is nothing but the voltage difference between the potential of these 2 points. That means 0 minus V0 by R2. So here I prime is equal to 0 minus V0 by R2 or RH. Here I have denoted the feedback resistance, the RF. So it is RF. So that is equal to minus V0 by RF. So you compare these two equations, and you can write here minus V0 by RF is equal to V1 by R1 plus V2 by R2 plus plus Vn by Rn, or V0 is equal to minus Rf into V1 by R1 plus V2 by R2 plus etc. to up to Vn by Rn. Now, if you consider that these resistances, these resistance R1, R2, Rn, all are identical, and all have the same value, that is equal to R, then you can write on this relation that V0 is equal to minus Rf by R into V1 plus V2 plus plus Vn. That means V0 is equal to minus Rf by R sum over Vn. Now, further, if you consider that Rf and R have the same value, then V0 is nothing but V1 plus V2 plus V3 dot Vn. Here with the negative, here negative sign will be here. So negative value minus of V1 plus V2 plus V3 dot Vn. So then the amplifier will act as an adder. That means it will sum of the input voltages. So OPAMP can be applied used as an to implement an adder or summing amplifier. Now further, we come another 2 points. Number one is if RF by R I, if RF by R is equal to 1 by N, if this ratio RF by R is made to 1 by N, then the output will be V0 will be minus of V1, V2, V3, etc. by N. That means this will be the average of the input voltages. So this amplifier then can be used as to average the input voltages. Furthermore, if all the voltages V1, V2, V3, etc. are made identical or equal, then V0 will be minus of V1 plus V1 plus V1 plus etc. That means V0 is equal to minus of N into V1. That means then the amplifier will perform multiplication of the input voltages. And you remember here, or you notice here, that here will be negative sign. Why here negative sign arises? Because the input, you have applied the input voltages to the inverting input amplifier. That's why the output voltage will be out of phase of the input voltages. So negative sign arises. Now come to the differential amplifier. Here the basic circuit diagram of a differential amplifier is shown, and in this type of amplifier the output voltage is nothing but the amplification of the different voltage which were applied to the input terminals. That is, if V1 is the input voltage applied to the non-inverting terminal and V2 is the voltage applied to the inverting input terminal, then this type of differential amplifier will deliver the output voltage which is proportional. You can say proportional to the different voltages, or amplify the different voltages. And here the voltage V1 is applied to the non-inverting terminal through a resistance R1, and then it is grounded through the resistance R2. Similarly, the input voltage V2 is applied to the inverting input terminal through the resistance R1, and then a feedback resistance R2 is connected between this point and this output and the point A. And the point A and B. Now come to the point A and B, and you know, and these 2 points later the potential of the point. This point is Vx, and at the point is Vy, and this will be equal, because in this case of this amplifier, the difference between the two input signals V1 and V2, since the open loop gain and the input impedance of the OPAMP are infinite. Open loop gain, this is the input impedance of this OPAMP is infinity, and also the gain is very high. So these 2 points A and B there will be a short circuit at the points A and B, and that means the potential at A and B will be identical, and let Vx and Vy at the potential at the points A and B respectively and are equal. Also, almost same current will passing through the resistance R1 and R2, and you can say form the Kirchhoff's current law, because no current will passing through this op-amp. So the current that will pass through the point A will also passing through the resistance R2 and go to the output. And here also the current that will pass through the resistance R1 will also pass through the resistance R2, and finally it will reach to the ground. So actually this current I1 and I1 prime will be equal, and in this case also I2 and I2 prime will be equal. Now let us calculate the values of these currents and also these currents. From this section of this diagram of this circuit, I1 can be found in this way, that I1 is equal to V1 minus this potential Vy. So I1 is equal to V1 minus Vy by R1, and I prime is equal to Vy minus 0 by R2, which is also written here, and these two are equal. So V1 minus Vy by R1 is equal to Vy minus 0 by R2. I write it as equation 1. Now also from this part of this diagram of this figure of the circuit, that I2 is equal to V2 minus Vx by R1. V2 minus Vx by R1, and I2 prime is equal to Vx minus V0 by R2. Vx minus V0 by R2. This is the equation. These two currents will be equal. So this is equal to this, and this is equation, and write it as equation number 2. Now subtracting this equation number 2 from equation 1, what you will get? Now subtracting equation 2 from equation 1, you will get that V1 minus Vy minus V2 plus Vx by R1 is equal to Vy minus Vx plus V0 by R2. And since Vx and Vy are equal, so you write from this equation that V1 minus V2 by R1 is equal to V0 by R2, and then V0 is equal to R2 by R1 into V1 minus V2, and thus the circuit amplifies the difference. And from this relation you easily understand that this amplifier amplifies the amplification is nothing but R2 by R1. So amplifies the difference voltages applied to the inverting and non-inverting terminals. So this amplifier therefore amplifies the difference voltage which are applied to the two terminals, and in this way the op-amp can be used as differential amplifier. Now come to the subtractor, the topic subtractor, and you see that for a differential amplifier, the output voltage is given by V0 is equal to R2 by R1 into V1 minus V2. Now if you make R2 by R1 identical, or if R2 and R1 are equal, then from this relation you can write V0 is equal to V1 minus V2. That is it. This equation straightforward gives the difference between the voltages that were applied to the non-inverting and inverting terminal respectively, and in such way a differential amplifier can act as a subtractor. So students, I hope that you understand the topics, and now you have to start it furthermore, and you have to practice all the calculations. Then all the matters will be easy to you, and you can understand what started here.